Hey everybody, I apologize I haven't been able to get this video completed. My voice is still healing up. Just a quick reminder, we have our midterm tomorrow. I will see you guys then. So last class we talked our way through electrophilic aromatic substitution, talking about disubstitution. This is where we're adding a second functional group to our benzene ring. We talked about reactivity strategies and some simple things like blocking groups needed, both to protect certain functional groups, or things like our acylation, but also adding things like the sulfonate group to prevent reactions in certain positions. So our first review question, if you look at these two pathways, take a look at the sequence we're putting them together. Is one possible? Is one impossible? So if you look at these two, in both cases, we're doing Friedel-Crafts acylation, adding an acyl group, and we're doing a nitration. In the first case, we add the acyl group first. Now that's both deactivating and also, so this is a deactivating group, but also it is meta-directing. So the next thing will go into a meta position. That's what you're seeing, this functional positioning here. So that's all possible. More importantly, even though the ring is now deactivated by adding this acyl group, the nitration will still work under those conditions. If we change the order of addition, this is once again deactivating, but at the same time, doing acylation, this one is not possible. If you remember, Friedel-Crafts acylation and alkylation is very difficult on deactivated groups. So even though it is meta-directing, even though the positions line up the way we want, we're not going to form this product because trying to do this carbon addition is very difficult after we've deactivated the ring by a nitro. So you have to actually put the carbon in first, then do the nitro addition. So A is the better route to do this. So today we're going to talk through the last part of electrophilic aromatic substitution and introduce aryl diazonium salts. This is another way to functionalize or add hetero groups to a aromatic ring. And then we'll introduce the concept of SNAR. It's a nucleophilic substitution onto aromatic rings. Now, if you look at a group like this is where we have a disubstituted starting material. And what we're asked to do is add a nitro group. And with both of these ones, if you actually look at the relative directing power, both of these alkyl groups are ortho-para directors. So for example, this isopropyl group will tend to guide things into the ortho or para position, and this methyl group will also be an ortho-para director. So this is one of those cases where both functional groups are guiding to the same three carbons. However, even when we do this, what you see is that there's a major component down here. So at this position, then you're getting a minor component over here, this position, and almost nothing over here. Now, this kind of substitution pattern is best described because of sterics. If you imagine, really, this one here is out because what you have to do is nitrate in between these two groups up at the top. That's very difficult. That means that this position is not going to be functionalized, mainly because we're blocking it by the two adjacent aryl groups. Now, if we're going to actually functionalize the other two position at this red center, this becomes possible just because we're next to a methyl. Compared to the isopropyl group up here, this is significantly more blocked because of the isopropyl group. The steric encumbrance there is larger. So you are seeing some selectivity just based on access to different carbons there, in addition to the ortho-para direction. So try to take this on. Imagine if you start from phenol and you wanted to make exactly this molecule in a couple of steps. What would you do? So first off, if we're starting from phenol and you look at what we're trying to make, both of these groups could be added by some kind of a Friedel-Crafts alkylation kind of step. Notice we're making a secondary center, so that matches what we could do for alkylation. However, we can't simply do something like aluminum trichloride and let's say an isopropyl chloride, that's going to fail. Directly in that component, what's going to happen is the Lewis acid will actually interact very strongly with your unprotected phenol. So the first thing we have to do is actually protect the phenol. We use something like an acyl chloride, and we can get the acylated functional group. So now that it's protected, it's still an orthopara director. Those are the preferred positions we're going to add to. Because of sterics, this will probably be the easiest to add if we're going to try and do like an alkylation to it. So although we've now taken advantage of the block or the protecting group from the acyl, we have a problem where we would actually target a center that we want to leave as a unfunctionalized center. So this is where we would apply our blocking group. So the next thing we're going to do is use something like our sulfonation. So that's their fuming H2SO4. What we can do there is we can sulfonate our aromatic ring, and that makes our SO3H. Now that it is protected, what we have is the activating center here and here directed, and once again the sulfonate here is going to be meta-directing to the same two sites. Even though it's slightly deactivating on the ring, the combination of the two will still allow us to carry this out. So the next step is to carry out two Friedel-Crafts alkylations using aluminum trichloride. And what that will do is get us to our properly functionalized product. We have our acyl group. We've added in two of these alkyl groups, and we still have our sulfonate SO3H. So now we just have to unblock it. Under weak dilute H2SO4 in water, we can desulfate. So our O-acyl and our two isopropyl groups. And then finally we can go through this next step. This would be like a saponification. You can imagine under acid or base conditions, but let's say we take sodium hydroxide and water and water methanol or something like that. That will get us to our final product where we lose the acyl group. Okay, so just a quick note about aromatic heterocycles. First of all, things like pyrrole with the nitrogen, furan, like you see below, thiophene, where this is actually a sulfur at the center. These are all very electron-rich aromatic heterocycles. Really what's happening here is if you look at this molecule, there are 6 electrons, but only 5 atoms for us to share them about. So relative to benzene, it's actually more electron dense, and therefore it's more nucleophilic. So what that means is we can do electrophilic aromatic substitution, but if you look here, now we have a case where, depending on which carbon we add to, so let's say adding to this carbon here adjacent to the hetero atom, or this carbon here. Now again, I'm just going to do by symmetry. These two carbons, the two red ones will give you one product, the two blue ones will give you a different one. And actually, there's a preference in this case. This first addition here is not the same. And you can look at the two and say, well, based on them, why would you expect one relative to the other? Now, in this case here, this carbocation is resonance stabilized via the oxygen. So you could draw this as an oxocarbenium, like this, O+, and that's really the only two resonance isomers that are available. We can't shuttle this out in other directions without losing or breaking our octet rule. So these are the two primary resonance isomers that are available if we were to add to this blue carbon over here. However, the red carbon presents us with another opportunity. So I can actually draw one resonance isomer like this, which puts it as follows. So double bond, hydrogen and E, and positive charge here. And there's actually one more that's possible now because of the lone pair on the oxygen. So I can get this geometry. So as a result, attacking at the red carbon produces a resonance stabilized carbocation that's spread out over 3 atoms rather than only 2. So red would be preferred. This will be the preferred addition site just because of a more stable carbocation intermediate. So it's really following the same kind of procedures we talked about for our ortho-para direction. So moving to the next topic, we're going to talk about our aryl diazonium salts. Now a diazonium is what you see here. It's this diazo group attached to our aryl. Diazo, if you notice, what this looks like is basically nitrogen gas. So N2 is a nitrogen triple bond neutral. Effectively what you're doing here is you're taking an aniline, and under these conditions, what we call acidic sodium nitrate, we can actually make this diazo species. This is typically done at very low temperature and usually with only a dilute or a very light amount of HCl. We'll talk about that mechanistically in a second. Effectively what we're doing is we're making a new nitrogen to nitrogen bond to make this diazo compound. And these are amazing reactions. Once we have this, we can use this as a very powerful electrophile. It's a way of us adding nucleophiles to our aromatic ring. Just one quick note, these salts are exceptionally dangerous, even though once you form them, usually use them immediately just because they do provide explosive risks. Now, if you imagine why this might be a problem, it comes down to what that chemistry is. I'll show you just in a second. Now, how we actually make the diazo goes as follows. We start with the nitrite, so this is where we start off with HONO or HNO2. That's our nitrous acid. Or we start with sodium nitrate. Often the reagent we start off with will be simply the sodium nitrite. Sodium nitrate under weak acid can be protonated to give us our HONO or nitrous acid. That molecule of nitrous acid, if we're under acidic conditions, it follows the similar pattern we've seen with these other electrophilic activations. We lose water by second protonation, so adding another proton to this oxygen center gives us a good leaving group, which then what we're doing is effectively ejecting that water group to give us our nitrosyl cation. Now these nitrosyl cations are very powerful electrophiles, so they can be added with other sort of lone pairs. So once we've taken our sodium nitrite in the presence of acid makes our nitrous acid. Nitrous acid with just a little bit more acid makes this solution of nitrosyl cations. So what's happening here is these are, remember, they're very powerful electrophiles, and as long as we treat something like an aniline that has a lone pair, that will actually attack at the nitrogen side. So what you're doing is this very rare reaction where we're doing a nitrogen to nitrogen attack because effectively this is a delta plus nitrogen. So that generates our first intermediate. We've made a nitrogen to nitrogen bond, and we have our 2 hydrogens. By doing this, we're going to be changing the charge, and it's NO. Like this, we've now satisfied out that final charge. So you can see kind of what the pattern is going to look like. What we're doing next is a series of proton transfers where through some kind of a proton transfer, we're going to be removing a proton from the cationic side and gradually adding them over here to the oxygen side. What we're really going to is I'm effectively eliminating water to make more bonding relationship between the 2 nitrogens. So it's a single bond and we're going up to a triple bond. We're going to lose the protons here and we're going to be losing the oxygen as well. So the proton transfer is going to set us up for the next bond formation, we're going to have our NH, N, double bond O, H, positively charged. And then after this formation, you can imagine that we could draw this as a tautomer again. If we're going to sort of move this, shoot. So after a proton transfer, what we're going to do is just lose the proton from the positively charged center to get us back to a neutral compound like this. Now, if you look closely, what we have here is a hydrogen and a almost like a carbonyl. So that's almost like an enol. You can kind of think of it. In this case, this is the carbonyl form, which means I can do a tautomerization, moving that hydrogen over this oxygen and moving a double bond in between these two centers. So that might look something like this, where we're tautomerizing this. And that's going to get me nitrogen, double bonded nitrogen, OH. So we're just representing this as a a nitrogen-hydrogen bond, and an NO double bond is becoming a nitrogen-nitrogen double bond, an OH bond. So it's that same kind of like an alpha deprotonation from a ketone to an enol. After that tautomerization, now what we can do is we're set up to lose water over here. So if we imagine another proton transfer step where we're going to protonate on that distal oxygen. So now we are nitrogen double bonded to nitrogen, OH2 plus, and we have our lone pair here. We can actually use that lone pair to help drive both the formation of this triple bond and lose water. So what that gets us to is our final compound. It's our nitrogen triple bonded to nitrogen, and we have a positive charge resident on this internal species here. And again, it's driven by the formation of water to give us our final compound. So this is just a good copy of that mechanism. Again, think of it as first electrophilic nitrosyl compound being attacked by the nucleophilic lone pair. That forms this cation, which we then get to a neutral compound. Tautomerization moves it to this OH, and then protonation at that center sets us up for losing that as water to give us our final compound. Now, what can we do with these? Well, remember we still talked about these being potentially explosive molecules. What's happening here is once we've formed these diazonium compounds, really that there is nitrogen, just happened to be attached to benzene. So we have a really good leaving group. This is something that wants to do bond breaking here to make us lose this thing and basically give you effectively an aryl cation. So you can think of this where equivalent loss of nitrogen gas, a really, really powerful leaving group, helps to make a carbocation. Now, this is not your normal carbocation. This is not a resonance stabilized carbocation because, in fact, the orbital, this lone pair here, this vacant plus, is actually in the sp2 orbital. It's kind of like, remember, if you have pyridine, in a pyridine molecule, this lone pair sticking out here is in an sp2 orbital. It's the same sort of thing. We already have the aromatic bonding across here, which means the cation that's sitting on that center is actually sitting outside the ring. And effectively, it's a ridiculously unstable carbocation. That means that capturing it is very much like an SN1 type reaction. You're making a carbocation where then almost any nucleophile you want can then be substituted in. So this is where the power of the strategy comes in. It allows us to take simple aniline molecules, turn them into amazing leaving groups, and then get us access to an aryl carbocation, which then can allow any nucleophile we want into that position. So it's a surgical way that if I have a nitrogen on an aromatic ring, I can sub it for almost any nucleophile I feel like. So that's summarized in these coming slides. It allows you to do all kinds of very simple transformations where, again, think of it where any nucleophile you're looking for can be plugged in. So if you're looking for an OH, you would be using water as your nucleophilic species. For many copper salts, in fact, do a really good job of acting with your salt, whatever the X minus component is, being added directly in. So this is how you would add cyanide by using copper nitrile or copper cyanide. You can add nitro this way too. So this is the nucleophilic addition of nitro, not the electrophilic addition. Remember, electrophilic, you would use something like NO2 plus, which you generate from fuming nitric acid. This is an example where what we're actually adding is NO2 minus. It's a negatively charged species where your positive cation is your potassium. If you need to add fluorine, you would use a molecule like HbF4. You can think of HbF4 as proton and BF4 minus. This is a source of equivalent to basically F minus as a donor. It happens through decomposition at the boron center, but effectively it allows you to substitute nucleophilic fluoride into a center. And again, this is one of the first reactions that we've encountered that allows us to install a fluoride into an aromatic group. Almost any copper salt, as I mentioned before, including things like copper chloride, copper bromide, allow us to put halogen into that center there. So this could be bromine or chloride. Iodide is typically done simply with potassium iodide, where you're just adding this source of I minus into the system. Lastly, you can do things like sulfur addition. This is through a potassium salt of a thioester. So this is your S minus kind of source to give you your sulfur addition. There can be additions of what's called azide. So this is potassium azide, or this is the N3 minus species to give you these components. Or finally, you can actually delete this whole group by the addition of phosphoric acid or even like an alcohol. These are cases where what happens is proteolytic decomposition, where we're actually installing a hydrogen where that whole group used to be. So the good side, this is a very universal way of installing a nucleophile into a system. We can actually take an aniline, reformat it, and add almost any nucleophile you want in a very predictable and very specific way. It's a very useful way to get very specific substitution patterns. However, it makes synthesis a little bit tricky, because what you're saying is almost any functional group could have gotten there from either electrophilic addition or now nucleophilic addition, what used to be an aniline center. In order to recognize where you've used the diazo, you have to look for things like these nucleophilic fragments. These are often how they're installed, is via the diazonium salt. So it can be a little bit tricky looking at how to do this by synthesis, but we'll practice a couple cases. Okay, so for example, if I wanted to make this molecule from benzene, it's not as easy as you think. If I took this and let's say, oh, I'll just use bromine and let's say AlBr3, okay, I can monobrominate this. That's not a problem. But if you remember, once I put one bromine in, this is actually an ortho-para director, which means the next bromine would be adding here, here, or here. That's not the pattern we're going for over here. So we would end up where the tribrominated molecule would actually have sort of a substitution pattern, something like this, not this kind of 135 kind of geometry. So it's not by direct bromination. We got to try something else. This is a case where what we can do is actually start off from benzene, and let's say we nitrate it first. If we nitrate it, sulfuric acid, we start with nitrobenzene. Nitrobenzene, we can use hydrogen and palladium on carbon to give us the aniline. All right, so, and we're not quite ready to go yet. If we have our aniline, the last step, we have to acylate it. So this is where we would take something like acyl chloride, and we could generate this. So this is now ortho-para activating, and it's now capped off where we aren't going to have a problem with the lone pairs in this nitrogen. Now we could go through and do our tribromination. This is something we could do bromine, AlBr3. Now, it's true that if we go through this component, each of the halogens that we're adding on are technically ortho-para directors. However, they're mildly donating versus something like this, which is much more strongly. So generally, what we're going to get, both based on sterics and based on the donating capacity of this amide, we will get preferentially the tri-substituted product where there are 3 bromines flanking this amide. So great, we've gone through this process of activating the ring, protecting the group. Now we've added our bromines. Now what we have to do is actually remove this group, and that would be something like hydrolysis of this center to get us back to the aniline. And in fact, we just want to remove that nitrogen altogether. So this is where if we treat it with, let's say, sodium NO2 and weak acid, we can diazotize it. So let's say this is dilute HCl, for example. What we would make is now, put it up here, we're going to make the bromine, and N2 plus. Last step is to treat this with something like methanol or ethanol. So alcohol will help us to protease this, and that'll get us this final component where that last hydrogen was actually installed by simply proteolysis of the benzene ring, of the diazosome compound. So take a moment, try to look at a compound like this and figure out what you might do in order to install this particular substitution pattern. So I'm going to list out the steps, and I would like you to try and draw out the components. So first would be nitration. So H2SO4 with HNO3. After we've nitrated it, next thing we're going to do, so again, starting from toluene in this case. So toluene, let me just draw that real quick. Toluene is your methylbenzene to begin with. So first we nitrate it, then we reduce the nitro group, so hydrogen over palladium on carbon. After that, we're going to acylate once again. So this is capping off that acyl group with maybe pyridine. And we now have a donor group on there. What we're going to do is so what we're going to do is we have multiple directing groups. So as you've noticed from this one, if you draw this one out, at this step, you're going to have a molecule that looks like this. You have methyl, nitro, which is now this acyl group like this. Now down here, this is going to be ortho-para directing. Up here, this is also ortho-para directing. However, this is a more powerful director. This becomes the likely site that you're going to add to. So in that second one, what we're going to do is nitrate it once more time. So that's H2SO4, HNO3. And that nitration will selectively go ortho to your amide group. After you've done that, what we have to do is cut the acyl group off. So this is where we would use something like water, HCl, and heat. And we're going to do the acidic hydrolysis of that amide. That'll give us back an aniline, where the next step after that is to convert it to a nitro. So this is our sodium NO2, and HCl dilute. So this is our diazo formation that'll convert the aniline into a diazo group that links it into a leaving group, and we can now do a nucleophilic addition of our NO2. That's where we take potassium NO2, which is effectively our NO2 minus reagent. It allows us to nucleophilic substitute what used to be the diazo, which would be down in this group here. So the next topic concerns the formation of these, let's say, nucleophilic substitutions. Now, if you have to do a nucleophilic substitution where we've got a leaving group like this halogen, and we're using something like this, like an O-methyl nucleophile, this does not happen via what we call an SN1 or SN2. This is actually doing what's called a nucleophilic aromatic substitution, or an SNAR reaction. So under these conditions, what happens here is if you have a leaving group, which is either para or ortho to a very, very strong electron withdrawing group, it's possible, but it has to specifically have that type of relationship. So you need these two components. You have your nucleophile and your leaving group, but more importantly, there's an electron withdrawing group on the aromatic ring, which is either meta to the leaving group or, ortho to the leaving group, like here, or para to the leaving group, like here. Only those substitution patterns work. I'll show you why mechanistically. What's happening in this case is if you've got that substitution, there's a slight delta positive at this center. If the nucleophile adds to that group, what we can actually do is by resonance, or by a conjugate addition, we're basically bumping that charge down. I'll show you just first of all, this first addition, the way we would draw it is adding to the center where the leaving group is, like this, and then bumping over the charge from that double bond. What that complex now looks like is going to have our nucleophile, our leaving group, and our nitro. And I'm going to draw the nitro out, shown like this. So from here, we have a positive charge sitting on that, a negative charge sitting on the center temporarily. We can actually slide that over by resonance to this center here. So we have a resonance structure, which we can draw like this, where we've got two substitutions, the nucleophile and the leaving group up here at this side, and we now have our electron withdrawing group. Remember, it's a nitrogen plus and a negative charge hanging out right there. What that means is we can actually use that center to slide that charge out even further. So there's another resonance structure that's allowed, which would look kind of like this. We call this a Meisenheimer complex. I'll show you how that on the next slide. So now, because of this nitro group, we have this series of other electron withdrawing participation where we're pulling that negative charge. The required negative charge we form from this addition is actually being stabilized by delocalizing out via the pi system. It's only because we can do this and form this charge that allows us to allow this chemistry to happen. So we're stabilizing the negative charge we're forming, and then how we would get to our product is simply by collapsing that tetrahedral intermediate. So this is shown out over here. In the para position, you can imagine a nucleophilic attack where that's fully coupled down, almost like an extended conjugate addition out to that center that forms you this, what we call the Meisenheimer complex. And then that can then collapse back, where we're pulling all that charge back, pushing all the way through to eject the leaving group out the other side. And that re-aromatizes the ring as we eject this leaving group. If it's in the ortho position, we get very much the same type of contribution. Nucleophilic addition here can be pushed out and then up onto this oxygen to give you this Meisenheimer complex, where we have the double bond now ex situ outside the ring. And then once it collapses back, it slides over and kicks out the leaving group to give us back our complex. But once again, if you focus right here, this addition along this path looks very much like the addition we had in the last chapter for Michael addition, where we have a nucleophile adding to the double bond over and up. It's the same kind of pattern that you're seeing here, and just this down here is an extended version of that same type of a system. So what's going on here? If we put these together, you notice that the leaving group is ortho to our electron withdrawing group. If we were to do this addition, this is my nucleophile. The nucleophile will attack at that center to form a Meissner complex, which would look like this. Double bond NOO double minus. And we will have a chloride and the nucleophile over here like this after, let's say, a proton exchange. That means that we're going to come down, over, and out, and our final product will just be the aromatic ring where we've substituted this group over here and our NO2 back over here. Now for this one, what we're doing is taking a carbon-centered nucleophile. Remember, this is our enamine. Now, enamines are nucleophilic at this alpha center. So what's going to happen is we're going to bring down the charge. That's going to attack at our center, which is going to push the charge. Once again, we have a leaving group, which is both ortho here, but also para here. These are very good electrophiles because they have double stabilization throughout that system. So from that component, we're going to get a nucleophilic attack between this carbon and this carbon. So highlighting just that addition, between those two centers, we're going to get our aromatic ring. And this is after the Meissner complex and then addition. We have our Meissner ring, NO2, like this. This is that carbon. We've now made a new bond over to our second piece, or second fragment, which is this six-membered ring. And that carbon is the one that corresponds to our starting material. Adjacent to it would be our iminium. If you follow the arrows out, we would still have this kind of a center, where final step is to hydrolyze this in dilute acid, and we get to our final ketone. So that will remove the imine to give us our NO2 bond, our six-membered ring, and our ketone.